Welcome to Module 1, Radio Systems Design on Basic Definitions. Today we're going to be talking about some very simple definitions for the beginning of this course. Time versus frequency, the concepts of dB, dBm, and dBc, and a little bit on filters. So the time domain is what we think about and we perceive in our everyday life. So in our world, time marches forward and we think about things happening over time. And so the time domain is very comfortable and familiar to us and typically is represented by a plot versus time. Not much to say in here, but if we think about the other domains we work with, namely the frequency domain, this is a little bit different. The frequency domain is an abstract concept that we've generated that really helps us deal with signals in a more robust way. And these are representing the signals by the frequency components that make them up. If you remember from the Fourier series that you can take any time waveform and break it up into a series of cosines and sines, and the frequency domain just simply plots the magnitude and phase of those cosines and sines that when you add up create the time domain signal that you are interested in. And we generally represent this in F, or we can also talk about omega. Typically as engineers we talk about F because all of our instrumentation is in frequency directly. Omega is used quite often because oftentimes analytical calculations end up in radians and omega is more useful. So we can go back and forth between the two almost interchangeably. The only thing you need to make sure of is that if you're doing a calculation, it may likely be in terms of omega, and if you want to convert to F, you need to use the formula right here. Alright, so the question comes in, if we have time domain is what we see in real life, if you will, and frequency domain is this concept, how do we measure these two? And so you should know that there's two primary instruments that we're going to use to measure time and frequency domain. So let's start with the time domain. And this is a picture of an old oscilloscope, but you probably already know that we use the oscilloscope here to represent the time domain, and so the time axis is actually right here. And then of course if we want to do the frequency domain, we use a spectrum analyzer where this axis right here is in terms of F, and these are simply plots of the magnitude of each frequency. Now we're going to learn to use both of these. It's expected that you probably already know how to use an oscilloscope, and we're going to go over some of the basic functionality of a spectrum analyzer and also go into some of its advanced features, because one of the things about radio systems is that we deal with signals of very low magnitude and are very low power, so microwatts, maybe even picowatts, and it turns out that we have to use some of these advanced features in order to be able to see these really small signals. So we'll talk about that more as time comes along. Alright, now we've been talking about the time versus frequency domain, and as you know we can go between those two using the Fourier transform. And so the Fourier transform will take us from a time domain signal into a frequency domain signal, as you know. And just as a reminder, if you change a signal in one domain, it gets changed in the other domain. However, the change is not the same. If we change this signal here, x of omega does change, but the change happens through the Fourier transform. So except for linear multiplications by scalars, changing x of t, for instance, shifting in time, does not just simply shift that on the axis, but this should be review for you. And so here is a couple examples of Fourier transforms, and one of the things we want to show you here is sort of how things look in the time domain and how things look in the frequency domain. So if you remember, the Fourier transform of a square ends up with a sinc function here, and you're probably familiar with that. If we were though to take a low pass filter, and I'll draw that in the frequency domain, so imagine I put in a filter that has a pass band like this. So it's pretty easy and intuitive from the frequency domain to realize we're just going to basically filter out all these sides, and this is the signal we get. But you need to remember that in the time domain it has an equivalent one, and it smooths it out. And we could have actually thought, about this directly in that a low-pass filter is going to remove all the sharp edges and smooth things out. So here's a great example of how operating in the frequency domain here is very easy and quick, but there is an equivalent time domain change that we just need to keep in mind. All right, so I've shown on the left a time domain waveform, and on the right it's Fourier transform. And just to be accurate here, I know that this right here is a cosine because it has two positive delta functions, so I would need to set my 0, for instance, right here to make this exactly accurate. And so we often say that a sinusoid is a single tone because it contains a single delta function in the frequency domain. And we also need to remember that all real signals have a negative frequency component as well, or it's sometimes called an image. And so whenever you look at the frequency domain, you should always see the image if it's a real signal. Now I should just be real careful. By real here we mean we can measure it in the lab. Okay, I specify that because we're going to be talking a little bit later about real and imaginary components in terms of in-phase and quadrature, and that just has to do with the fact that we're using imaginary to represent a 90-degree phase shift, but those are both signals we can measure in the lab. So real here is more of just realistic or stuff we can measure in the lab as opposed to real and imaginary. So I want to talk a little bit more about this negative frequency. If you actually did the Fourier transform of a cosine, you would see that one of the coefficients comes out and it has a minus j omega t component, and that's what gives us this delta function. Another way that I think helps me remember two things, one is what this is, and also that we need both, is this identity here you probably remember. If you think about these as plotting e to the j omega t, and this is e to the minus j omega t, right? We know that e to the j omega t is cosine omega t plus j sine omega t. So if I just had one of these, this is what I would get. I'd get a real part and I'd get an imaginary part. So I wouldn't have a completely real signal. If I want a completely real signal, what I need to do is combine two of these, either for a cosine or a sine, and what that does is it creates either a cosine or a sine and removes the imaginary component. So if you think about this plot simply as a e to the j omega plot, it helps me out a little bit in remembering why I need both. It's because I need this to be real, and that we can think about a cosine here simply as these two components right there. All right, I want to talk now about the concept of dB. Now, I always use the example of temperature to kind of explain why in some engineering fields we have all these different units. And the reason is let's take temperature for example. We have the Celsius scale and we have the Fahrenheit scale. And so the Celsius scale is based upon water, right? 0 is freezing, 100 is boiling. The Fahrenheit scale, I don't know if you knew this, but the Fahrenheit is actually based upon the human body. So 0 to 100 is supposed to be the temperature range that humans can inhabit. And so Fahrenheit is based more or calibrated more on the human body. So I always say if you ask what the temperature is outside, it's more useful to know it in Fahrenheit because you're asking about what it's going to feel to you. But if you're looking in a scientific endeavor, we need some reference to have common amongst us, and water is a fine reference, so Celsius is good. So why am I telling you this? I'm basically saying that people use different units and different measuring methods based upon what they're doing. So if you're going through your engineering career and you come up with a new terminology, or in particular a new measurement unit or a measurement scale, and it's foreign to you, it's likely because there's a different concept that you haven't encountered before, and the fact that there's a new measurement unit or scale is an indication that that is an easier way to understand this new concept. So instead of thinking I have to learn a new unit, you should be thinking about, this is a flag that something new is coming conceptually. And so dB is something that you've probably encountered before. dB is very useful to make comparisons for multiplication. And we use the log scale often because we can have signals that are as low as a picowatt or as high as a kilowatt in wireless systems. And so that's 10 to the 15th. So 15 orders of magnitude change in signal strength. So you can see with that kind of change using a logarithmic scale can be very helpful. And I just wanted to give you a quick reminder. If we do log base 10, by the way, everything we're going to do is base 10 unless I say otherwise, of x times y, and you probably already know that's simply going to be log of x plus log of y. By the way, this is how people used to do multiplication in the olden days. The slide rule would take the log of a number, and then you would add the two logs, and then you could take the inverse log and get the product. Just a couple other real quick ones. Log of 1 over x is simply minus log x. And then, of course, log of x to the n is n log x. Okay? dB is a logarithm based upon 10, and we write dB is simply 10 log 10 of the number. Now, we use 10 because in RF systems we're primarily dealing with power. In signals and systems you probably did a lot of work with 20 dB in 20 log, and that happens because those are voltages and currents rather than power. And the reason we're using the logarithms is because it's an easy way to do calculations. I do want to stop you here and just do a quick brain teaser. What is the log of x plus y? Think about this for a second. This is something that we will test a number of times and people often get stuck on. The log of x plus y is simply the log of x plus y. The key here is there is no simplification. Okay? It's when we multiply do we get this nice simple form. If we're adding, we don't. So to do this properly, what you'd actually have to do is add x and y in the linear domain and then take the log of that. And sometimes we might give you x and y in dB, and you would have to convert those to a linear domain and then take the log. So for instance, if, just do an example, x equals 3 dB and y equals 10 dB, all right, so I want to go through a couple examples. One of my colleagues put together a nice system of dB 1 through 10. So the log of 1 is just 0, so we get 0 dB. 1 dB is equivalent to 1.25 in the linear scale, and I'll just let you follow along. Pi over 2 is 2, 2 is 3 dB, 2.5 is 4, pi is 5. By the way, if you're wondering why pi is magically 5, please notice that these are approximations. We're just using pi because it's convenient and it's close. If you do this exact calculation, it's not exactly 5. So there's no magic here. It's just we all know pi is roughly 3.14 and it's easy to remember. 4 is 6, 5 is 7, 2 pi is 8, 8 is 9, that's kind of interesting, and then of course final one, the log of 10 is simply 10. Now this is kind of a fun exercise, but there's really only 3 numbers you need to remember. Okay? 10 is 10 dB, that's easy to remember. 0 dB is 1. So 0 dB is the same as the same. What this means is if I take a signal and I multiply it by 1, I haven't done anything to it, so there's a 0 dB change. and 3 dB is the same as 2 times. And this is probably the most used one because we'll think about it. And it's pretty easy because 3 dB is twice, 6 dB is 4 times, and 9 dB is 8 times. So you can kind of move through this pretty quickly. So why are we dealing with power? Previously, you probably looked at voltage and current because that's what you can measure with an oscilloscope probe or in a simulator. But why in wireless systems do we deal with power instead of voltage? And it turns out that it's kind of actually difficult to measure voltage and currents at high frequencies. And so what is easy to measure is power. So once again, this is going back to my sort of Celsius Fahrenheit. We're talking about power here because it turns out that's what we deal with mostly in the lab because that's what's easy to measure. There's voltage and currents is running around just like any circuit, but we talk about power because that's what's easiest to measure. The other aspect is that most signals are random. And it may sound a little confusing to you, but the carriers that we'll use, cosines and sines, they're not random. But the data we put on most communication signals is random. And the best way to think about that is if you're talking to your friend on the cell phone and you look at the bits that come out of it from your conversation, they're pretty random. And so if we're looking at a random signal, we can talk about its random properties. But the average power of that signal generally stays the same. So if I'm looking at your cell phone signal coming out, I probably can tell you exactly what its power is over the entire conversation. It'd be really tough unless I captured exactly all the data to figure out what exactly the voltage and currents were. So this is another reason why power is useful. And just a few things here. It's easy to measure. And the easiest way to measure power is actually just by putting the signal into a resistor and measuring its temperature. And that's actually how we do it. We actually have a resistor, we put the signal in and we measure the temperature change, and that'll tell us how much power was in that signal. And the only thing we need to know in the temperature change is what the value of the resistor is. And for convenience, we choose 50 ohms. And the reason why we choose 50 ohms is for the case of power, we could choose any resistance, but 50 is a number we choose once again because it's a useful impedance in the RF world. At home, if you remember the cables that would connect your TV to the cable television, they're coaxial cables, those generally come in 50 ohms and 75 ohms. It turns out that if you're going to build a coaxial cable, the highest power transfer, the most efficient power transfer would occur when that cable is 30 ohms, and the best voltage transfer would happen when that cable was 75 ohms. And when I mean 75 ohms, it's the characteristic impedance of the coaxial cable, which is a transmission line. We'll talk about that later. The reason I mention it now is, do we use 30? Do we use 50? Turns out 30 or 70. It turns out 50 is a nice approximation between the best power and the best voltage. And so that's generally why we have settled on 50 ohms as a standard for transmission lines. Because it's a standard for transmission lines, it's also the standard for instrumentation, and therefore we measure power in terms of 50 ohms. So there's a little bit of a background on why 50 ohms. And let's just look a little bit at how we would calculate power from voltages and currents. So, so when we actually do a lot of our design calculations, we're talking about voltages and currents. And when we talk about power, we have to assume that we're driving a 50 ohm load. And so when I ask you the power in a signal, I'm assuming it's driving a 50 ohm load unless I don't specify this. And this can lead to a lot of confusion because most papers don't even mention the fact that there's an assumption of 50 ohms. You just need to remember that. And so let's do a quick example. This is a low noise amplifier. It's basically an amplifier, and the output of the amplifier gives us a 632 millivolts. So this might be what you measure on an oscilloscope or in a simulator. And we want to know what the power of that signal is. Well, to calculate the power, you can think about this is just a buffer of 1 and putting it into a 50 ohm load and figuring out what the power of that would be. All right. So let's just look at this real quick. We've got 632 millivolts. Okay, so this is 1/2 of 632 millivolts. Okay, but that's the peak, right? Do you remember what the RMS is? The RMS is going to be 1 over the square root of 2 of that. Okay, and the power is simply equal to V squared RMS divided by R. So I'm going to take this and I'm going to square it, and I'm going to end up with 1/8. That's because I get a 2 from this and a 4 from this, times 632 squared divided by 50. And if you calculate that out, that's 998 milliwatts. Okay? And so if we're looking at a signal, we're assuming it's driving a 50 ohm. And so if I tell you the output of the LNA is 998, or about 1 watt, you could go and back calculate what the voltage is. And in fact, on a spectrum analyzer, if you want to know what the voltage coming in is, the spectrum analyzer is telling you what the power it's receiving is, and you just do the same calculation with 50 ohms to figure out what the actual power is. All right, so we talked a little bit about dB, and it was helpful when doing logarithms, but dB really is telling us a ratio. So when we say something is 10 times, we're saying, let's just take an example here. If I have an amplifier and I have P out and I have P in, if I say the gain is 10 dB, that means that P out over P in is equal to 10. Okay? So we're generally in dB dealing in ratios. In fact, we're always dealing in ratios. But sometimes we want an absolute value. And so what we're going to do is we're going to find an absolute value in power. I'll just skip through here. By defining a reference point. So for Celsius, we say water is a reference point. And for dBm, we simply use 1 millivolt as our reference point. And so what this means is that we basically say, what is the ratio of P out to 1 milliwatt, and that would give us dBm. Okay, so just as an example, 998 milliwatts. Okay, this is not an equal to 10, so this would be 10 log base 10 of 998 milliwatts divided by 1 milliwatt, right? And so these would obviously cancel, and I'm going to take 10 log 10 of 998, and this is approximately equal to 10 log 10 of 10 to the 3, and this is equal to 30 dBm. Okay, so dBm is giving us an absolute power because we have an implied reference of 1 milliwatt, whereas dB is giving us a ratio. Typically of a gain, and in wireless systems we're often talking about power, so it's a ratio of gain. It's important not to mix dB and dBm, and also when X is in dBm and it's amplified by Y dB gain, the final power is X plus Y dBm. Why is that? Well, imagine that I've got a signal coming in to an amplifier. Okay. If its power gain is Y and the input power is X dBm, the output power is going to be, if you will, sorry, let me erase that. The output power is simply going to be Y times X. Let's say Y was a factor of 10, then it would just be 10 times. And I want to stop you for a second and think about something a little bit different. What would happen if I had the output of 2 amplifiers, Y1 and Y2, and I now add them? I'm doing this contrast so you can see the two. Here we're multiplying, so we are adding, sorry for that, we are adding our logs. Here we're adding in the linear domain, so what would the output be if Y1 and Y2 are in dB? Well, we're going to have Y1 dBm plus Y2 dBm But remember, we can't, because the actual operation here is summation, what we have to do is we actually have to change this into y1 linear. And so the way we would do that is I would say 10 Okay, now if we remember, dBm is 10 log 10 of P over 1 milliwatt. So what I would do is I would take y1 and I would divide it by 10, and I would take all of that to the 10th power and multiply it by 1 milliwatt, and that gives me y1 in linear, and I would add that to 10 to the power y2, 10 times 1 milliwatt, and that would give me the linear power out here. So this would be P out in a linear. And if I wanted to put that back in dBm, I would just go back to this equation. So you can see that in multiplication, like for a gain stage, we're adding the dB, but whenever you're adding signals, you've got to go back into the linear domain. And we're going to test you on this several times because it's something that we often forget. I got a quick summary here just to get you on the same page. dB, it measures the ratio of two things such as gain and attenuation. Once again, in RF, we generally do this in terms of power. dBm gives you an absolute measurement, and we reference it to 1 millivolt. And I just wanted to give you one more example that kind of helps you understand the naming convention here. dBc. This measures the power of a signal referenced to a carrier. And so oftentimes when we're transmitting a signal, we'll have our information and then we'll also have our carrier signal. And we'll sometimes talk about that power of the information or the other frequencies to that carrier. And we just use the same thing. Here it's referenced to 1 milliwatt. Here it's referenced to the carrier. And so the example is if the carrier is 5.3 milliwatts and the signal is 5.3 microwatts, what is the dBc of the signal? And it's simple. We're just going to take 10 log base 10, 5.3 microwatts divided by 5.3 milliwatts. And this is just 10 log 10 of 10 to the minus 3, and this equals minus 30 dBc. So you can see we can take this and reference it to anything we want. There's nothing magic about dBm, it's just we're talking about power. All right, the final thing I just want to talk about is a filter. Typically, we're going to measure this in terms of omega or F, and if we're doing this in terms of dB, we're talking about the P out over P in. And a couple things I want to point out. We have our center frequency, omega naught. This right here is our bandwidth, and we'll call this delta omega. Now, if we take delta omega over omega naught, this is our relative bandwidth. Another convenient one is if we take omega naught over delta omega. This is what you probably remember as being Q. We talk about Q for resonators, we talk about relative bandwidth for filters, but it does the same thing on the plot. And the last thing I just want to point out to you is that the top of a filter is never exactly equal to 0. And that's because there's some insertion loss. And that's measured by this, and this will typically be minus something, maybe 0.5 dB, meaning we lose a half a dB of power due to the insertion loss of the filter. This should be well known to you, but just wanted to kind of cover it for completeness. All right, so this completes Module 1 on basic definitions. We talked about time versus frequency domains, dB, dBm, and dBc, and then we also did a quick review on filter specifications.